Okay, good morning again. So we are starting our lecture. And let me recall that in the previous lecture, we have considered quantization of electromagnetic field in the Coulomb gauge. And what we have done, we have constructed the quantum theory of the free electromagnetic field in the Fock space. And then we consider also the case of including the sources. And we have found that the Lagrangian or action of the corresponding theory is non-local. It contains a Coulomb interaction energy. So the Hamiltonian contains the Coulomb interaction energy, which provides a non-local contribution in the corresponding Hamiltonian. So a couple of remarks about this is that, in fact, quantizing electromagnetic field, we have performed quantization only once. In other words, we don't need what we call second quantization. It's already a kind of a second quantization of a classical electromagnetic field. And this is a difference with Klein-Gordon and Dirac field, because those involve H bar already at the first quantized theory. Which, as you remember, at early stages of quantum field theory, was regarded as a Schrödinger equation for a single particle. So these equations, I mean Dirac equation and the Klein-Gordon equation, at the early stages of development of quantum field theory, were regarded as a Schrödinger equation for a single particle. Now, we know that Maxwell equations do not involve H bar at all. So in a way, they describe truly classical fields. Now, in the Coulomb gauge, we have also seen that the corresponding theory describes only physical degrees of freedom. But unfortunately, the Lorentz invariance is not manifest because the corresponding Coulomb gauge is not Lorentz covariant. And nevertheless, one can show that the theory is Lorentz invariant, and this can be done by explicitly constructing the generators of the Lorentz algebra in terms of transverse oscillators and checking that indeed these generators actually commute as the generators of the Lorentz algebra should do. We can also discuss that the photon field does not transform under Lorentz transformations as the vector. And that is because Lorentz boosts destroy the Coulomb gauge, and one needs to perform a compensating gauge transformation to restore back the gauge condition. So these are all the features, I've just repeated them once again, which we find when we quantize electromagnetic field, and in particular, we quantize in the Coulomb gauge. Now, today, I will talk about another important physical quantity, such as the helicity of a photon, and then I will come to the so-called covariant quantization, which tries to overcome the difficulties, in particular the difficulties with non-locality, which one meets in the Coulomb gauge. So let's talk about a helicity of a photon. Now, since the action of electromagnetic field is invariant under Lorentz transformation, then in accord with the Noether theorem, there should exist the corresponding conserved charges, and they must form the Lorentz algebra. So the invariance with respect to Lorentz transformation is obvious because, as you remember, the action is written as -1/4 integral f mu. So indices are contracted in a Lorentz covariant manner, and therefore the action is invariant with respect to Lorentz transformations. So it's not difficult to write down the corresponding Noether currents and the Noether charges. In particular, well, this is an exercise for you to do this, particular for generators of three-dimensional rotations. You will find from the Noether theorem the following expression. I will write it already in the quantum theory as a normal ordered operator. So Gij is 1 over c squared, c is the speed of light, dx, so three-dimensional integral, and then we have ak dot xi dj minus xj di, ak dot means normal ordered product minus, again, normal ordered product of the other term, ai dot aj minus aj dot ai. So this is the generators of three-dimensional rotations. So indices I and J run 1, 2, and 3.
I'm sorry, did we already define the Fock algebra for electromagnetic field?
Which algebra? Sorry, which algebra?
The Fock algebra, to define normal ordering.
Yeah. So normal ordering goes absolutely in the same way, or is defined in the same way as for the Klein-Gordon field. All creation operators are standing on the left from all annihilation operators. So for the case of the electromagnetic field in the Coulomb gauge, we know that we have two transverse oscillators, two transverse annihilation operators, and two transverse creation operators. We have seen the commutation relations between them. That is something which I have written in the last lecture. Remember, A and A dagger for different polarizations, they commute on the delta function and delta Kronecker of polarizations, and A with A and A dagger with A dagger do commute. Then you pick up a vacuum state and construct a Fock state in a standard way by acting with creation operators on it. And normal ordering means, again, that's one and the same thing. If you write these fields A and A, yes, A in terms of just creation annihilation operators, and these two dots means the same thing. All creation operators go to the left from all annihilation operators. Then these generators will annihilate vacuum state. So the action on the vacuum state is well defined. So vacuum is invariant. Vacuum is annihilated by this generator, so it's invariant with respect to three-dimensional rotations. Okay?
Yes.
Okay. Now, it turns out that for electromagnetic field, the stress energy tensor, if you derive stress energy tensor, again, by using the Noether theorem, you will find out that it's symmetric. So T mu nu is equal to T nu mu. So electromagnetic tensor is symmetric. Now, as a result, it means, if you remember our discussions in the previous semester, this means that the orbital part of the total angular momentum, so this you can consider as generators of angular momentum, by the way. No, as usual, three-dimensional rotations generate angular momentum as a conserved current. So this means that the orbital part of the angular momentum is conserved separately from the spin part. And this part is exactly what I call orbital part. So let me maybe write this, just put here the red line and say that this is orbital part, and this is a spin part. So orbital part, you see, it contains this characteristic expression xi dj minus xj di, and you recognize in this expression exactly the generator, quantum mechanical expression for the generator of angular momentum. And then there is the spin part, which does not involve spatial derivatives, just involves indices I and j of vector potential. Okay, so there is an orbital part and the spin part. And they're separately conserved. Let's see how we can maybe show this in a more explicit way. For that, it is sort of convenient to introduce separate notations to call, say, orbital path, generators of orbital path by Lij. So this will be 1 over c squared integral dx double dot ak dot di xj xi dj minus xj di ak double dot, and then there will be orbital path Sij. I define it with a minus sign like this, ai dot aj minus aj dot ai, and therefore the total angular momentum Gij is Lij plus Sij.
Professor?
Yeah.
So what does it mean physically if we have a photon, if it rotates in an orbit?
Well, that's what I'm going to explain what it physically means. So photon is a particle, as you know, of spin 1. So that's why it is described, to describe it, you need this electromagnetic potential, which carries index mu. And so this means that it transforms under Lorentz transformations. Well, if there would not be imposition of any gauge, it would transform as a vector. But then we also impose, say, a Coulomb gauge in this case, and then it has rather non-trivial transformation properties under Lorentz transformations. And the fact that orbital path is separately conserved from the spin path, you can actually verify in 1 second just by taking, say, Sij and differentiate it with respect to time. So let's check this in a very explicit way, that it's conserved. So you get minus 1 over c squared integral dx, and then here you get ai double dot. I just differentiate with respect to time this expression here. So ai double dot aj plus ai dot aj dot minus aj double dot ai minus aj dot ai dot like this. Now these two expressions actually cancel, and what is left over is the following thing. So potentials actually commute, because it's like electric field minus electric field. So these two, we know components of electric field do commute, so that's why these two terms cancel. And what is left over is minus 1 over c squared dx. And then we know that field AI in the Coulomb gauge satisfies the wave equation. And from the wave equation, we can replace the double dot by just derivative with respect to second derivative with respect to spatial directions. So by Laplacian, in other words, so this I can write as wave operator, I can write as AI double dot minus nabla squared AI, like this, equals to 0. And therefore I can replace this double dot with two derivative. Well, this operator is, if you wish, I can write it as dk or simply dk squared sum over k. And therefore here, what we see is dk squared ai aj minus dk squared aj ai, like this. And now, if you integrate this by parts, so you put 1 dk to aj, then the result of this integration will be actually 0, because then you get 2 equal terms, and this term is equal to this one, and therefore they cancel. And so this explicitly shows that indeed the spin part is conserved. Now, you can also define the dual three-dimensional vectors, dual to Lij and Sij, by using the standard trick with epsilon ijk tensor. So you take Ljk and pair it with epsilon tensor, and then you get a vector Li. And the same is with Si, 1 over 2 epsilon ijk sjk. So you have a three-dimensional vector of angular momentum. This is Li, and you have also vector Si corresponding to the spin part of the angular momentum. Now, since the Coulomb gauge condition which we impose on our vector potential does not break three-dimensional rotational symmetry, you see, with respect to index I here, there is a covariance. You sum up over index I, so I is 1, 2, 3. So this condition, the Coulomb gauge condition, is invariant with respect to three-dimensional rotations. Therefore, we expect that the angular momentum tensor or the corresponding vector, which we write as 1/2 epsilon ijk gjk, we expect that this three-dimensional vector must satisfy the standard Poisson bracket relations of the angular momentum. Or, if you wish, in the quantum theory, the corresponding it should satisfy the corresponding commutator for components of the angular momentum. This means, for instance, that in the classical theory, if I just now come back to classical theory, then these components must satisfy the condition ji jj is equal minus epsilon ijk jk. And this relation, of course, you know very well from quantum mechanics, right? These are how components of the angular momentum commute commute with respect to the Poisson bracket. So Poisson bracket of gij gives you epsilon ijk multiply epsilon ijk multiply with jk with a minus sign in front. So this is algebra, Poisson algebra of angular momentum. Let me ask, is it familiar formula for you from quantum mechanics? Or whatever. Yes. Familiar formula, very good. So this
Sir, could you repeat this part again?
Yeah, so what I'm saying is that you see that Coulomb gauge condition, which we impose on components of our electromagnetic potential, is a condition which preserves the three-dimensional rotational symmetry. I can rotate my field AI by means of three-dimensional rotations, and the Coulomb gauge condition will be preserved, so it will not be destroyed. And if this is the case, then what we expect from the tensor of angular momentum? No, we expect that its relations between its components are standard, should be standard relations between the components of angular momentum. So in particular, with respect to the Poisson bracket, this formula in this box must be satisfied. Okay, that's what I'm saying.
Okay, thank you, Professor.
Okay. On the other hand, you see from this expression here that the Coulomb gauge condition mixes the spin path and orbital transformations. It means a spin and orbital transformation. It mixes spin and orbital transformation loss, because here this index I on A is responsible for spin transformation properties, while this derivative is responsible for orbital transformation properties. Yeah, so this derivative acts on the argument x of the field AI, while index I here is responsible for spin transformations. So in other words, the Coulomb gauge condition somehow mixes the spin and the orbital transformation properties. And if it mixes the orbital and spin transformation properties, then somehow it indicates that for components, individual components of L and S, we will not have the standard relations. Standard relations, you would expect that components of the orbital momentum will transform as epsilon ijk lk, and the spin would transform as si sj minus epsilon ijk s k. And so also spin and orbital generators or spin and orbital transformations separate. So Poisson bracket between them is equal to 0. In fact, this is, as I'm saying, this is not the case exactly due to the condition that the spin and orbital transformation properties are mixed due to this imposition of the Coulomb gauge. So this is not correct. And this is not correct. And this also will not be correct because spin and orbital transformations know about each other. And therefore, actually, they Poisson non-commute, if you wish. So, yeah.
Yeah, can you repeat this last part?
So last part, I'm saying that from spin and orbital angular momentum, you should not expect the standard algebras. The standard algebras you would normally expect from just experience with angular momentum. So you naively you would say, well, I have a spin part and I have orbital part, and I know that they separately conserved. And so what is orbital part? This is just standard angular momentum. And spin is also standard angular momentum, if you wish, in an internal space. So naively, you might expect that these two transformation laws, these two transformations, spin transformation and orbital transformations, do not know anything about each other. They behave themselves separately. They are separately conserved. And therefore, each of them must satisfy the standard algebra of the angular momentum. And the fact that they do not know anything about each other would be signified by this bracket, Lisj is equal to 0. And I'm saying that this is not the case. This is not the case precisely because the Coulomb gauge condition mixes the spin and orbital transformation properties. That's what I'm trying to convey with these equations.
Also, can we say it like this, that the total angular momentum should be conserved, not the individual?
No, of course, total angular momentum is conserved by the Noether's theorem. This generator we derive by using Noether's theorem, and of course by Noether's theorem this is conserved. Now we know that if in the theory the stress energy tensor is symmetric, then in fact we can say a little bit more about conservation of angular momentum. We can say that its orbital path and spin path are separately conserved. And now if this Jij is conserved, and we have shown explicitly that Sij spin path is conserved, then of course orbital path is conserved as well. Of course, you can verify it by direct calculation again by taking this orbital path, differentiating it with respect to time, and you will see that due to the equation of motion for electromagnetic field, namely this box equation, the result will be the conservation law for the orbital path. Okay, so yeah, angular momentum, of course, total angular momentum is of course conserved by, no, but this is direct consequence of the Noether's theorem that it's conserved. And the fact that separately orbital and spin paths are conserved, this is a consequence of the symmetry of the stress energy tensor.
Okay.
Okay, and but now there is nothing which prevents us from computing this Poisson bracket between Li, ln J and Si and Sj explicitly, because we know the Poisson brackets between components of the electromagnetic field and its time derivative, which is electric field. We know these are canonical Poisson brackets which we have discussed in the previous lecture. And if we apply these Poisson brackets between components of electromagnetic potential, we will find actually the following algebraic relations, Poisson relations between Li and J. The relation will be as follows: Ijk minus Lk plus Sk. You see this shows that L and S are non-trivially interact in a way. Lisj is not equal to 0. This is minus epsilon ijk sk, and this is the same as silj. And finally, you will find out that SI, components of S, they commute between themselves. This is a result of direct computation. Yeah.
So this is the reason why we say for an electron in an atom, we say as LS coupling. LS.
Yeah, so you see, L's themselves, although they are responsible, they are generators of the orbital path, their Poisson bracket is not closed. It involves also contribution of the spin path. So in other words, spin orbit coupling, there is a non-trivial spin orbit coupling, and so they are not separated, spin from orbit. Interactions, they are not separated. And this is what is responsible. I'm trying to repeat again that what is responsible for such a structure is a Coulomb gauge condition. This is where all this comes from. Now, this is a result of direct computation. The computation is a bit tedious because the Poisson bracket between the components of electromagnetic potential and electric field is non-trivial. You know, it's non-local. It involves the inverse Laplacian. But you can find the corresponding computation, which I'm saying is not completely trivial, in my lecture notes. So if you wish, you can repeat it, or you can look in the lecture notes to see why and how this Poisson structure of L's and S's is reproduced or can be derived. In any case, this is how it looks like. This is how it looks like. And now I'm coming to the issue of polarizations of photons and the notion of helicity for a photon. So turning back to the quantum theory, in the Coulomb gauge, we find that this SI, given as 1/2 epsilon ijk as jk, can be written in the following way: -1/c² integral dx. Let's write in this way: epsilon ijk aj dot transverse a transverse k double dot. So in fact, if you come back to this initial expression here, multiply it with epsilon tensor, you take spin part and multiply it with this part here, multiply it with epsilon ij, then you will see that actually only transverse part of electromagnetic potential contributes, and longitudinal part completely decouples from this expression. And that's why you see here only contribution of the transverse component of the vector potential. And for this transverse component, the corresponding expression I have written down in the previous lecture, so you remember it when we discussed expansion of the electromagnetic field in terms of oscillators. We have written down an explicit form for the vector potential. Maybe I quickly repeat it. So a transverse vector depending on x and t is given by some prefactor integral dk divided by square root of 2 omega on k, and then there is a sum of polarization vectors where index r runs 1 and 2, so 2 transverse polarization vectors, and then oscillators exponential minus I omega t plus I kx plus AR dagger on k exponential I omega t minus I kx. Right, so this is an expression which we have stated in the previous lecture. Now take this expression for the transverse component of the electromagnetic potential, substitute it into this formula here, and commute, bring everything to the normal ordered form, because bring oscillators to the normal ordered form, because here you have double dots. That means that you put all creation operators to the left from all annihilation operators. Now, if you do that, then you find in terms of oscillators the following expression for SI. It's an exercise also to do, just substitute. And then these polarizations, I mean, you need to sum them up, and they are summed with the help of the following formula. So the following formulas are useful in order to derive the final expression for SI. So let me write them down, because without these formulas, you will not be able to make this computation. So epsilon IMN, epsilon tensor, epsilon MR on K, epsilon NS on K gives Ki divided by modulus of K, epsilon, let's see, IRS. I guess what is left over here. No, this should be, so I'm summing over index M and N. So this is summed up. Then index I is on the left-hand side, and then it's on the right-hand side, R and S. So this is delta RS. And then there is another formula, which is also useful and needed in order to, so this is, yes, standard epsilon tensor. So this epsilon tensor is with 3 indices, and polarization vectors, they are with 2 indices, one up and another is down. And so there is another formula, IMN, epsilon tensor, polarization MR on K, and here polarization with inverse momentum, so NS minus K is equal to Ki modulus of K 1 minus delta RS. So these formulas you can derive by taking into account the explicit form of the polarization vectors, which I have written down in the previous lecture. If you take Z expressions and explicitly compute such pairings with epsilon tensor, then you will find exactly this right-hand side. Okay, so with these relations of summation of these polarizations with epsilon tensor, then you can easily compute what is SI. And for SI, in terms of oscillators, you will find the following expression. So this will be integral dk, epsilon 3 depending on K. So the third polarization vector, which is directed along the momentum of a photon, A2 dega on K, A1 on K, minus A1 dega on K, A2 on K, where this third polarization vector, now vector index, I write as index I, that is given by the following expression, that's Ki divided by modulus of K. So this vector, epsilon polarization vector epsilon 3 is directed along the vector K. So if you wish, I can also write it like epsilon 3 is K divided by modulus of K, like this. And this is also, I think I'm writing this not quite correct. So this is a vector. So S is a vector with components Si. And you see vector on the left-hand side, and this is a vector on the right-hand side. It's directed, so vector S is directed along K. So if you remember, polarization vectors, we were writing like this, epsilon 1, epsilon 1, say with low index, epsilon 1, epsilon 2, and epsilon 3. And then direction of propagation of electromagnetic wave is vector K, is along vector K. And now epsilon 3 is actually collinear to the vector K, and epsilon 3 has a unit length. So it's a north directed exactly in the same direction as a vector of momentum vector K, which describes the direction of propagation of electromagnetic wave. Now, let's consider a one photon state. So what does it mean is that, as we discussed, we have a vacuum, and to this vacuum we apply the creation operator. This R can be either 1 or 2. So we create one photon, apply this creation operator, so one photon state. And now we act on it with a vector S. And let's try to see what we get. So in other words, what we are trying to do, we are trying to measure a polarization of this vector AR plus acting on the vacuum. Polarization of the one photon state. Well, this action is easy to compute. You just take this expression, which is in the normal ordered form, and then you see that this is AR plus, if you specify R to be equal to 1, let's specify now. Say first, let's take this R to be just 1. Then we see that this A1 plus will not commute only with this expression here, with A1. Yeah, because there is a non-trivial commutator between these two oscillators. And the result of this commutation will be minus IH bar epsilon 3 on K A2 dega on K acting on the vacuum. And analogously, if you take S and act on A2 dega vacuum, then the result will be IH bar epsilon 3 on K A1 dega on K 0. So in other words, this operator S acts on our one photon states not in a diagonal manner. So A1 plus goes into A2 plus, and A2 plus goes to A1 plus. In other words, this operator in a way mixes A1 plus with A2 plus. But you can actually diagonalize this action. If you now consider, say, combine this into column, so if you allow me to omit this vacuum from the left and right hand side, then this action can be in fact written in the following way. So you take A1 plus, A2 plus, acting on this vector S, and then the result is H bar epsilon 3. And here there is a matrix 0 minus I0. So off-diagonal matrix, again acting on A1 plus, A2 plus. Now, if you act with this matrix, you see that you exactly reproduce these formulas here. Do you have any questions here? If this is flow of logic is clear to you?
What is the physical meaning of
what? Of S?
No, not of this. I mean, of this of S acting on creation on one particle states in such manner.
Yeah, so what we are trying to do here, we are trying to measure the helicity. So S will become what is called helicity. Helicity of a photon, as you will see now.
So helicity is spin.
No, helicity is a projection of spin on the direction of motion. So you see, spin in this case, again, is not very good notion, probably, because again, this is due to the imposition of the Coulomb gauge, which mixes orbital and spin properties. So they are kind of intertwined. But helicity is exactly this operator S. And what I'm trying to do is now is the following. I will try to diagonalize this section to find eigenstates of this operator S. You see that A1 plus and A2 plus, this one photon states with linear polarizations, they are in a way not eigenstates of this operator S. S acts in a way off diagonal. It mixes A1 plus and A2 plus.
So do I understand it correctly that one particle states with circular polarization eigen?
Yes, exactly. That's exactly what I'm going to say now. Is that this is Pauli matrix sigma 2, as you see, right? So this is sigma 2. And you can easily diagonalize sigma 2 by the following transformation. So take matrix Q, which is 1 minus I, 1I. And then this matrix diagonalizes sigma 2. So Q sigma 2, Q minus 1 is a matrix which is 1, 0, 0, minus 1. You can check this. And making therefore the following linear combination of oscillators A1 dega and A2 dega like this. So you take A dega right to be 1 over square root of 2 A1 dega minus A2 dega. A dega left. Here is I. Here I need I because yes, this matrix which rotates, sigma 2 contains I in it. So A1 dega minus I A2 dega. Q left will be not Q, sorry, AL dega will be 1 over square root of 2 A1 dega plus I A2 dega. No, and analogously, you introduce right and left oscillators for annihilation operators. So 1 over square root of 2 A1 plus I A2 and A left 1 over square root of 2 A1 minus I A2.
I'm sorry,
So,
where did we get the matrix of Q from again?
this is a matrix which diagonalizes sigma 2. Okay, so I just found it as a matrix which diagonalizes sigma 2. Not more, not less than that.
How did you find here AR, AL diagonal?
Well, you see that if you take this column A1 plus and A2 plus and apply to it this matrix Q, you will get exactly new components, which are this AR plus and AL minus. Yeah, you see, you take Q
yes.
and act on A1 plus, A2 plus. So basically, you take this expression here and you rewrite it in the following form. So S is an operator. So matrix, which is numerical matrix, passes through it. S is an operator, so it does not see this matrix. So you rewrite this as S Q A1 dega A2 dega. On the right-hand side, you get H bar epsilon 3, which is a vector which has nothing to do with this matrix sigma 2. So you get Q acting on sigma 2. Q acting on sigma 2. And here on the right-hand side, you write QQ minus 1 Q acting again on A1 plus, A2 plus, right? So this becomes diagonal, 1, 0, 0, minus 1. And this becomes your new oscillators, AR plus, A plus L, and here is the same, AR plus, AL plus, like this. So in other words, you may introduce the following operator. Say, in order to get rid of this epsilon 3 directed along the momentum, you can introduce the operator of helicity, that's actually the operator of helicity, as a projection of S, which you might call spin, on the direction of motion, epsilon 3 on K, because this is a unit vector directed exactly along the momentum of our electromagnetic wave. So it's a projection of spin on the direction of propagation. And so then it is clear that if I now consider the action of action of this helicity operator on my oscillators, even if I forget about the vacuum and just compute the commutation relation, then these oscillators commute with this helicity operator in the following way. If I restore H bar, then this is right oscillators produce in a way the eigenstates of the Helicity operator with eigenvalue +1, and analogously, if I take AR minus and the corresponding relation, A left plus, right and left plus will give me minus H bar A left plus. So in units of H bar, the projection of spin on the direction of motion is +1. And in this case, people call this photon right polarized photon. Right polarized photon, polarized photon. And that means that if this is roughly our photon and it propagates in this direction, so its momentum is k, then projection of spin on the direction of motion, that's helicity, is equal to +1. And analogously, -1 is a left polarized photon. Polarized photon, for which situation is different. So k is in this direction, while j is in opposite direction, and this is left polarized photon. It has polarization -1. And in fact, these polarizations, they correspond to circular polarizations. That's what we call circular polarizations. And in one case, in a way, right photon is polarized in one way, and another photon is, direction of polarization is opposite. You can also introduce complex polarization vectors. If you want to describe this circular polarization in an explicit way, you can introduce the vector ER, which mixes two linear polarizations like this. And this is, probably you can read about this more, for instance, in the book of Landau-Lifshitz, how this circular polarization is described. But mathematically, this is exactly what I'm doing here. I'm mixing with this index, with this imaginary unit, these two polarizations to produce linear polarizations, to produce circular polarizations. So they are related by the following conjugation condition. And then you can re-expand electromagnetic potential, its transverse path, where these circular polarizations, which are eigenstates of this helicity operator, with eigenvalues ±1. So sum goes over index R, taking either right or left values, and then there is this, let's write this as a, let it be right epsilon and left epsilon, and then there is this right epsilon AR, depending on k, everything depends on k, exponential minus I omega t plus I kx, like this, plus ER. Here I should write the lower index R, which takes value either R capital or L capital. So the same is here, but conjugate. AR dega on K, exponential I omega t minus I kx.
I'm sorry. Could you also please explain the components of the vector potential, the transversal and the longitudinal components of the vector potential? They are transversal and longitudinal with respect to what?
They are transverse and longitudinal with respect to the action of the derivative di. So what we know is that the component is transverse if it satisfies this expression. And this is what we call transversality. So this is what is implemented in this expression for AI dega. And that's why these oscillators, which come into two polarizations, so A1 and A2, and A1 Dega and A2 Dega, these oscillators, which we call transverse oscillators. Transverse oscillators, because they enter in the potential, electromagnetic, actually vector potential. There is no scalar potential, vector potential, which satisfies the transversality condition. So transversality is with respect to action of this derivative di. In other words, this transverse path satisfies the Coulomb gauge condition. This is the way we implement the Coulomb gauge condition in an explicit way. And that is clear why, because when we act with derivative di, momentum, we act on x, therefore momentum k gets down, but these vectors, epsilon 1 and epsilon 2, they satisfy the condition that their scalar product with k is equal to 0. That's the way how we constructed our orthogonal frame. So vector epsilon 1, epsilon 2, and then k, which is orthogonal to this epsilon 1 and epsilon 2. And that guarantees the satisfaction of the transversality condition, which is the same as the Coulomb gauge condition. Okay?
Yes.
Mm-hmm. Okay, and you can also check that this change of variables. So this is simply a linear change of variables, what we have done. And you see that it's such, you can check this by explicit computation, that A Dega R AR plus A Dega L AL is the same as a sum from R from 1 to 2 of the original oscillators. Sorry, R here. So that comes by using these formulas here. If you multiply AR Dega by AR plus AL Dega by AL, and this square root of 2 is introduced on purpose, so that this expression here is, this equation here is satisfied, and the satisfaction of this expression actually allows you to rewrite the physical Hamiltonian of electromagnetic field, which is the same as energy of electromagnetic field, where creation operators of circular polarized photons. So sum R from R and L, AR on K, AR on K. So it's the same quadratic expression, but now instead of linear polarized oscillators, there will be circular polarized oscillators, which are linear combinations of linearly polarized oscillators. Okay, that's all what I wanted to tell you about helicity of a photon. We understand now where does it come from. It comes from the Noether's theorem, general expression for angular momentum, where we see that orbital and spin path separately conserved. Now we take spin path, work it out. We saw that it depends only on the transverse component of electromagnetic field. We see that this SI, SJ commute between themselves, Poisson commute, or commute in the quantum theory. And then we act on the one photon states with this operator, and we realize that actually we can diagonalize this section, introduce the notion of helicity as a projection of S on the direction of propagation, and we see that we can introduce then a concept
I'm sorry.
Right polarized photons and left polarized photons. Mm-hmm.
In the second formula from the bottom, on the right hand side, is it true that both operators should be with pluses?
Oh, no, sorry. I'm too fast. Of course not. Of course not. It's the same quadratic form, A plus A, but now written in terms of linearly polarized oscillators. So in other words, Hamiltonian can be written either in terms of linear oscillators or in terms of circular polarized oscillators. And expression is all the time is a quadratic form A dagger A sum over polarizations. Okay, if you don't have any further questions concerning helicity, notion of helicity, where does it come from? Then
can we measure helicity experimentally?
Yes, of course, yes. Because you can measure polarization of light, and I think in principle on the physical faculty of Moscow University there is such an experiment.
I mean, okay, is macroscopically, is helicity the same thing as polarization?
Yeah.
Or
yeah, it is. It is. It is. And actually, when you have, you know, sometimes in summer, you buy and very what is called polarized spectacles, right? Polarized spectacles.
You mean polarized filter?
Polarized filter or polarized spectacles, which you which you carry when in a sunny day.
I also graduated from a physical faculty, so I had
yes. Okay. Yes. And that means that when your filter is tuned to a particular polarization, then this is exactly what you in a way physically measure with your eye. It comes to your eye, and the other polarizations are invisible to you because polarizations say fluctuations of electromagnetic field go in the other plane, and that's why this filter does not see them. But if you tune it in a different way, you will see other polarizations. And so you can measure that actually there are two independent polarizations. Either you consider them as linear polarized things, or taking the linear combinations, you can get circular polarization like we are discussing here, for instance. Yes, these are two physically measurable, quantity. And that's what you do with the help of polarized filters. Okay, now let's come to the issue. Yeah?
Can I ask something? Because I remember when we studied Dirac theory, we saw helicity, but there it was a concept depend on the Lorentz frame. Here,
yes, but here it does not depend with respect. It does not depend on the Lorentz frame for a simple reason, because photons propagate with the speed of light.
Perfect. So here is.
And yeah, and then helicity has an absolute meaning because yes, we don't have a Lorentz frame where we can sit on our photon and change the polarization. That is impossible. So it has an absolute meaning for photons. That's because they propagate with the speed of light.
Perfect. Thank you.
Mm-hmm. Okay, so covariant quantization. I would like to give you some idea. I cannot say that I will develop it in how to say in full details. By itself, it's quite a subject, but I will give you an idea and try to argue for its usefulness in a way. Now, in the case of an interacting theory involving electromagnetic field, quantization in the Coulomb gauge, as we know, leads to the action with non-local terms, and this is rather inconvenient. Also, imposition of the Coulomb gauge breaks the manifest Lorentz invariance. No, and then it leads to necessity to a posteriori prove that the quantum theory which you construct is Lorentz invariant. So non-Lorentz invariant gauge actually leads to Lorentz invariant theory. And therefore, it is actually desirable to develop a covariant quantization procedure, which at the same time circumvents the difficulties of dealing with non-local actions. And the starting point to approach this covariant quantization problem is to start from the so-called Stueckelberg action. Stueckelberg action, which is the following the following thing. This is an action which contains the standard electromagnetic action F mu, but then in addition to it, you add an extra term 1/2 lambda d mu a mu squared, where lambda is an arbitrary real constant. For the moment, it's arbitrary real constant. A little bit later, we will see that there are certain restrictions, but mild, very mild, on the possible values of lambda. Otherwise, it is arbitrary real constant.
It is here, Lagrange multiplier.
It's not even Lagrange multiplier. You can fix it to be, for instance, 5. You can think about lambda to be 5. So I can explicitly replace lambda by 5. It's just a constant parameter. So it's not a field. So it's not a field. That's why I'm saying constant. Constant, it means it's x independent, space-time independent. So it's just a constant. Some real arbitrary real constant.
I wanted to say something, but then I reconsidered.
Okay. This term, which you are adding here, traditionally it's called gauge fixing term. It's traditional name for the term you add to the standard electromagnetic Lagrangian. Now, adding this term reduces the gauge freedom of the standard Maxwell action. So we know that this, we call this action Maxwell, standard Maxwell action. We know that standard Maxwell action is invariant with respect to such transformations, right? Where alpha is an arbitrary function on a space-time. Now, when you add this term, then actually you see that if you compute, say, d mu a mu, then this will transform as to d mu a mu plus d mu acting on alpha. And this means that adding this term, we partially break the gauge invariance of the theory, because now we see that only those transformations, gauge transformations, which will not, which will survive from the general gauge transformations, will be the transformations which satisfy an equation d mu alpha. In other words, the box alpha is equal to 0. So the Maxwell action, original Maxwell action, is invariant with respect to transformations with any lambda, with any alpha. Alpha can be any. Now the new action is invariant only with respect to restricted class of gauge transformations, which satisfies this condition box alpha is equal to 0. Since these residual gauge transformations, I call them residual gauge transformations, satisfying this condition, are not generic, the kinetic term of the vector potential becomes non-singular and therefore invertible. So kinetic term becomes invertible. you remember previously we could not invert the kinetic term operator defining the quadratic path of the Lagrangian, in other words, and that lead to the problem of defining, for instance, the propagator for the Maxwell theory. Now there is no anymore such a problem, and we break the local symmetry of the Maxwell equation, well, at least partially, and what is important is that for a new action, all 4 components of the field A mu become propagating. So 4 degrees of freedom, 4 actual degrees of freedom of A mu become propagating. So
I'm sorry, do I understand it correctly that this is a special case of introducing a ghost field?
Well, it depends what you call by ghost field. What I'm trying to say is that now this action describes propagation not only of the transverse photons, as was before in the Maxwell theory upon imposition of the Coulomb gauge, but it actually includes contribution or propagation, if you wish, of the time-like photons and longitudinal photons. So in fact, all components of A mu become physical, become propagating. And the question, of course, is how to achieve agreement with the original Maxwell theory. Because you say, well, but now I don't have Maxwell theory anymore, right? I've modified my action and I see that this action describes more degrees of freedom than I know from the Maxwell theory, where physical photons are transverse and have 2 polarizations. So this theory is different. Apparently, this theory, upon introducing this term, is different from the Maxwell theory. And so the question is how to achieve an agreement with Maxwell's theory. And it turns out that in this covariant approach, the actual agreement with Maxwell's theory is reached only at the level of quantum theory, where 2 degrees of freedom corresponding to time-like and longitudinal photons are removed by imposing a special constraint on states in the Hilbert space. Write this. So agreement with Maxwell's theory is achieved by imposing a special constraint, on states in the Hilbert space. So what we see is that Hilbert space becomes extended, it becomes bigger because it will now incorporate also states corresponding to longitudinal and transverse photons. But on the other hand, what we will do, we impose constraint on this Hilbert space, which allows to cut out only the physical subspace which would correspond to the transverse photons. And therefore formulate a theory in such a way that its content would coincide with the content of the Maxwell theory, where we have only transverse photons, for instance, in the Coulomb gauge. Now, these allowed states from this subspace, this will be the states satisfying this constraint on the one hand, and on the other hand, they will describe asymptotically observed transverse photons with 2 polarizations and positive energy. Okay, when we come back to this Stueckelberg action, by differentiating by paths, considering this term f mu and differentiating by paths, you can see that it can be brought to the form 1 over c d for x minus 1 over 2 d mu a nu d mu a nu minus 1 over 2 lambda minus 1 d mu a mu squared. It's just written down explicitly electromagnetic tensor as f mu being d mu a nu minus d nu a mu. Then I multiply all the terms, integrate by parts, and then no, I even don't integrate by parts. What I've done, I just use the symmetry of f mu, that it's skew symmetric, and then from the skew symmetry, this coefficient 1 over 4 turns in 1 over 2. There will be also the term, extra term d mu, which will produce the shift of this lambda to lambda minus 1. So this is the same action as above. And from this, you can elementary derive equations of motion for a field a mu. And this equation looks as follows. So box a mu plus lambda minus 1 d mu d nu a nu is equal to 0. This is how the new equation looks like, and it depends on this lambda is on the parameter. That's a constant parameter we have. Now you see, originally we did not have lambda, so original Maxwell equation corresponds to the case when lambda is equal to 0. And so when lambda is equal to 0, we return back to the original problem with this operator, which we know is a degenerate operator. We can write it as a, well, this is the same operator as for the Maxwell theory. And we know that this kinetic operator, which we have here, box minus d mu d nu, box eta mu d mu d nu, is actually degenerate. So we, of course, exclude then point lambda is equal to 0. So when we consider lambda not equal to 0, then this kinetic operator in this equation becomes non-degenerate, and therefore it becomes invertible. It becomes invertible. Nice point, especially nice point, as you can see, is a point lambda is equal to 1. For lambda is equal to 1, actually, equation just becomes box a mu is equal to 0. What is also interesting, that this equation here for lambda not is equal to 0 implies the following. If I take this equation and heat it with the derivative d mu, I will get box d mu a mu plus lambda minus 1 box d mu a mu. So this means that I get here lambda box d mu a mu, and this must be equal to 0 as a consequence of this equation of motion. And therefore, when lambda is not equal to 0, so I'm not in the Maxwell theory, then equation of motion implies that box acting on d mu is equal to 0. From here, I cannot, however, conclude that d mu a mu is equal to 0. This I cannot conclude. D mu a mu might not be equal to 0, so I'm not reaching the Lorentz gauge. Lorentz gauge, Lorentz without T gauge, I cannot reach. Not that I cannot reach, but I just see that equation of motion does not imply it. It just implies that this combination d mu a mu satisfies the free wave equation. So box acting on it gives me 0. In other words, what I'm trying to say is that equation of motion, which we have obtained here, is not equivalent to Maxwell equations in the Lorentz gauge, because Lorentz gauge is not the one which we get from this equation. We just get that box d mu a mu is equal to 0. One comment is that, of course, you, as I said, you see from this equation that lambda is equal to 1 is a nice point, distinguished point, which makes equation of motion particularly simple. But on the other hand, you understand that if you do everything correctly, nothing should depend on lambda. So lambda is a more or less arbitrary parameter, arbitrary non-zero parameter, and therefore nothing actually should depend on lambda if you compute the physical quantities, like observable quantities, like, for instance, electric and magnetic fields, or combinations of electric and magnetic fields. And therefore, it is actually convenient to keep lambda in all the calculations, because decoupling of lambda from the gauge invariant quantities which you compute is in a way provides you a non-trivial consistency check that your calculations have been done correctly, because nothing should depend on the choice of this arbitrary parameter lambda. That's why I prefer to develop a bit this Stueckelberg theory by keeping lambda and not putting it directly equal to 1. Okay, so now...
Can you again could you repeat that point?
Yeah, I'm saying that I said that we start from Stueckelberg action where lambda is an arbitrary real constant. It can be pick up at your will. Whatever you like, you can put it whatever you like, except lambda is equal to 0. Because lambda is equal to 0, you are back to Maxwell equations, and then you have all the problems connected with this, sorry, with this equation. I can fix lambda to be a nice, to be equal to 1, which is a nice value, because as you see in this case, this term disappears and the equation becomes simply box A mu is equal to 0. Without any restrictions for each component of electromagnetic potential, you get free wave equation, which is nice. But on the other hand, I know that on this lambda should not depend anything concerning the gauge invariant observables. And therefore, I say that you can keep lambda to be arbitrary, not to put it equal to 1, but at the end of the calculation, this lambda must disappear. It must decouple from your computation. It must cancel out, because nothing should depend on the choice of this parameter lambda, provided it's not equal to 0. Okay, that's what I'm trying to say. And that's the reason why I would like to keep this lambda arbitrary as a parameter in the following computations, what I will do. Okay?
Okay.
Mm-hmm. Now, what I would like to do, I would like to develop a bit the canonical formalism, so to try to construct the Hamiltonian. And the first thing, as usual, you do is you derive canonical momentum, P mu. That is elementary to do. You differentiate with respect, Lagrangian with respect to velocity for the field A mu. And you will find that if you do that, you will find the following expression. Lambda minus 1 c squared A0 dot plus c di ai. This is derivative of this Lagrangian, which you see here, with respect to A mu dot. More precisely, A dot and mu with which is upper index. Then you get this expression here. Now, then we continue. It's a non-degenerate theory now. There is no problem. It's not a singular theory. You can express all the velocities via canonical momentum, and so you can construct the Hamiltonian in the standard way. So in particular, if you want to have a canonical Poisson bracket between P mu and A mu, then you start to build up again the Lagrangian in the phase space approach, in the first order formalism, as we call it. So you start from the term P mu on X, A mu dot on X, and then minus rest, whatever makes a difference between original Lagrangian and this kinetic term responsible for the Poisson bracket. And this rest is, of course, our Hamiltonian. It will be Hamiltonian, so it's a standard. In this case, since theory is non-degenerate, then this is a standard relation between Lagrangian and the Hamiltonian. And so then you find the following expression. So Hamiltonian is 1/2 integral dx and here you will get the following expression: minus lambda over c squared a dot 0 squared minus 1 over c squared ai dot plus di a mu plus lambda minus 1 di ai squared. This is how the Hamiltonian looks like, and if you wish, you can replace ai dot via canonical momentum. And so if you do that, then the Hamiltonian in terms of coordinates and momentum will look like this. So minus c squared over lambda p0 squared minus 2c lambda minus 1 over lambda p0 di ai plus c squared pi squared minus di a 0 squared, like this, plus di aj with upper indices, and plus lambda minus 1 over lambda di ai squared. Okay, so this is how it looks like. So you need some time to appreciate this expression. The Poisson bracket, according to this standard canonical form, is the bracket P mu on X, A nu on Y is equal to delta mu nu, delta function X minus Y, X minus Y, and what else should be said? So it is standard canonical bracket. The theory is non-degenerate, as I said. Therefore, Hamiltonian is constructed in the standard way. And what is interesting when you look at this Hamiltonian, you see that the quadratic form with respect to momentum, which we get here, is not diagonal because of this term here. Because of this term here, which couples P0 to diai, this form is not diagonal. This term can be removed by making shift P0 goes to P0 plus lambda minus 1 over c diai. If you make such a transformation, then you can remove such a term. But this transformation is not canonical. So it does not preserve the Poisson bracket. Canonical transformations are transformations which preserve the Poisson bracket, but this transformation here will not actually be canonical. And in order to be canonical, one has to supplement this transformation by the shift pi goes to pi minus lambda minus 1 over c di a0. I mean, non-canonicity of this transformation will be destroyed because of the bracket of pi with ai, because this have non-trivial Poisson bracket, then the canonicity will be destroyed unless you shift pi by di a0. But on the other hand, if you do this shift, then it leads to appearance of another non-diagonal term, which looks like pi di a0. So at the end of the day, trials to remove this off-diagonal interaction between p and a does not seem to be possible. I mean, I tried to work with this section quite a lot, quite some time, and I was not able to remove by any canonical transformation the off-diagonal terms. They always come back, whatever you do. So this means that maybe one should leave this idea of finding the transformation which diagonalizes it, but simply go and solve equations of motion for the electromagnetic potential. I think probably it is a good time to make a break here, and in the next hour I will tell you how to solve the field equations for electromagnetic field in an explicit way, equations which are these ones and which are coming directly from this Stueckelberg action. Okay, so my proposal is to make maybe 10 minutes break and then come back and consider explicit solving the equations of motion for electromagnetic field coming from this Stueckelberg action. Okay?
Okay.
Okay.
Okay. So, in the meanwhile, you might appreciate these formulas which I'm writing. These are quite new formulas. I think in almost none of the books treat this subject as I'm treating it here. So you can consider this as an original thing. And it's very interesting how things will be developing further with this covariant quantization.